I am going to talk about sparse regression via range counting. This is joint work with Jean Cardinal. In this work, we design approximation algorithms for sparse linear regression, sparse affine regression, and sparse convex regression. We attack those problems using elementary tools such as polyhedral distance, phase shooting, prune and search, and orthogonal range counting. The problems we study are generalizations of the nearest neighbor search problem. In this problem, we are given a dataset of points, let us call it D. Given this dataset, we want to be able to answer queries, where a query is a point and the answer is the data point closest to this query point. Why is it interesting to be able to answer such queries? Because this could be used in applications where you have data with labels, which are identified by colors here. A query would be a point without a label. A way to infer a label for this unlabeled point would be to give it the label of the closest data point. In this presentation, we are going to study algorithms for generalizations of this problem, specifically offline algorithms, where the data and the query are given simultaneously. We do not know the data in advance. There exists a long line of research to design efficient data structures for nearest neighbor search. This is not what we're going to look at. Note that a simple brute force offline algorithm solves nearest neighbor search in linear time. Here is a first generalization called the nearest induced line problem. As before, we have a dataset D and we want to answer some query Q. The answer to a query is the line induced by 2 points of the dataset that is closest to Q. This already looks more difficult than nearest neighbor search, which we could solve offline in linear time. Here, the number of candidate lines is quadratic, one for each pair of data points. Hence, a brute force algorithm is not efficient. Here is another example, a variant of the first generalization we just saw. In the nearest induced segment problem, the answer to a query is the segment induced by the dataset that is closest to the query point. Again, there are a quadratic number of candidates and hence the brute force algorithm is not efficient. There are more ways to generalize the nearest neighbor problem. Starting from the nearest induced line problem, where a line is defined by 2 data points, we could instead search for the closest plane defined by 3 data points, or the closest k-1 flat defined by k data points, or the closest hyperplane defined by d data points. We could also generalize the nearest induced segment problem by replacing the segment defined by 2 data points by a triangle defined by 3 data points, or a k-1 simplex defined by k data points, or a d-1 simplex defined by d data points. We can encapsulate all those different generalizations by a single definition depending on a few parameters. In constant dimension D, we fix a parameter k. Given a dataset D and a query Q, we wish to find a linear, affine, or convex combination of at most k data points that is closest to the query. When an affine combination is sought, we call this problem the nearest induced flat problem. And when a convex combination is sought, we call this problem the nearest induced simplex problem. These problems have already been studied before. In 2016, Harpelet, Indik, and Mahabadi developed a data structure for a 1 plus epsilon approximation of these problems, where the preprocessing time is roughly n to the k, and the query time is roughly n to the k-1. What we show is that it is possible to get rid of the preprocessing time. That means that we can solve the problem offline as fast as the cost of a single query in their data structure without having to preprocess the data. In this talk, we focus on the special case where k equals 2 and d equals 3. The explanation is visual, the result generalizes for the other cases, it yields a nice efficient approximation algorithm, and no other algorithm is known to achieve this bound. The first thing we need to do is to trade Euclidean distance for polyhedral distance. Imagine we put a point A at the center of a disk of radius 1. Then, the Euclidean distance between this point and another point B is the scaling factor that you need to apply to the disk for it to touch B. We can trade this perfect disk for an approximation, in this case a polygon. such that the scaling factor we need to apply, called the polyhedral distance, is bounded above and below by appropriate. The combinatorial complexity of this approximated sphere depends on the dimension and the approximation factor. Since we only care about cases where those parameters are constant, the polygon has constant complexity. This generalizes to any dimension. Given a point Q and a line F, the polyhedral distance between those objects is the scaling factor such that the scaled polygon touches F. This happens at a vertex of the scaled polygon. This observation generalizes for any D and K. To compute the polyhedral distance between a point and a line in 3 dimensions, we can use the previous lemma by shooting edges of the approximating polyhedron to see which line is hit first. Taking the minimum over all edges of the approximating polyhedron yields the closest line. Focusing on a single edge, we can find the closest line by a prune and search method. We start with some well-chosen initial scaling factor and look at all the lines piercing the triangle defined by the query and the scaled edge. If the number of such lines is 0, then we are done. Otherwise, we pick one such line uniformly at random, declare this line to be the current closest line, and recurse with a new scaling factor corresponding to the polyhedral distance to this line. This yields the closest line for a given edge of the approximation polyhedron in a logarithmic number of steps. This method works as long as we have an efficient way of sampling and counting lines piercing a given triangle. In the paper, we explain how sampling reduces to counting, so all that is left to do is to show how to count. One way to count how many induced lines pierce a given triangle is by brute force. However, this would defeat the purpose by already costing quadratic time. We proceed as follows instead. For each data point A1, we count how many other points A2 are such that the line induced by A1 and A2 pierces the triangle. The locus of these points A2 is the double cone of apex A1 defined by A1 and the triangle. For this approach to be more efficient than brute force, we need an efficient data structure to count those points A2. Note that in the convex case, the locus is the truncated lower cone. Now observe that moving the point A1 only rotates the supporting planes of the double cone around the supporting lines of the triangle. This means that the lower and upper cones can be described as the intersection of subintervals of cyclic permutations induced by those supporting lines. The problem of efficiently querying such intersections has a name: orthogonal range counting. To sum up, we have an algorithm where first we trade Euclidean distance for polyhedral distance. This costs us a 1 plus epsilon approximation factor. Then, to compute the polyhedral distance, we have to do phase shooting for each edge of the polyhedron, and there are only a constant number of these edges, depending on d and epsilon. Then, to solve the phase shooting problem, we use a prune and search method, which necessitates a logarithmic number of steps on expectation. Each step of this search consists in solving a counting problem. To solve this counting problem, we reduce it to orthogonal range counting, by noticing that each edge of the triangle defines a cyclic permutation on the dataset. Those permutations can be plugged into standard orthogonal range counting data structures, which can be built in n times log n to the number of axis minus 1, that is 3 minus 1 equals 2. This is perfectly balanced with the cost of querying the data structure for each data point, where each query costs log n to the number of axis minus 1, which is again log squared n. Overall, we get a running time proportional to n log cube n. In this talk, we presented an efficient 1 plus epsilon approximation algorithm for the nearest induced line and nearest induced segment problems in R3. In the full version of the paper, available on arXiv, you can learn how this technique generalizes to any parameters d and k. For the general case, we obtain an n to the k minus 1 polylog solution. In this paper, you also find a conditional lower bound that matches this generalized result up to polylogarithmic factors, an exact algorithm for the special case k equals d, and a more detailed comparison with previously known results. And as always, thanks for watching.